This is Sophie Kinney, and I'm a staff scientist here at VPix Technologies. One of my roles is to help clients identify the research equipment and accessories that they need to implement their research effectively. In this presentation, I want to talk to you about projection systems, an area where advice can be particularly helpful. Projection systems often involve much more complexity than one might expect. Let's imagine that you want to put together a vision experiment for human adult participants. You're interested in obtaining stereo acuity threshold. You have decided that you will conduct a 4 alternate forced choice task. In the central 20 degrees of a visual display, you want to set up a simple 2x2 grid filled with random noise patterns. In one of the grid's 4 quadrants, you will have hidden a depth-defined circle target. If the subject is able to accurately identify the quadrant in which the target is embedded, then on the next trial, the amount of depth disparity will be reduced and make the task harder. So even from this brief description of stimuli, you can see that there's one extremely obvious requirement for your projection system, that you'll need to be able to display computer-generated 3D stimuli based on your participants' response. So how can you do this with a projector? Well, throughout this presentation, I want to guide you through what I call the what, where, and how of projection systems. First, we'll explore what projector technology is, what different specifications you might need, and accessories for your research. Next, we'll discuss where you plan to conduct your experiments, because the physical space in which you plan to install your projector can set constraints on what's achievable, and it's important to look at it with a critical eye. And finally, we'll cover how to install your projector within this location to achieve your goals, and I'll highlight some common problems and solutions that are encountered in small testing spaces. By the end of this presentation, I hope that you'll find a newfound appreciation for how the details of projection installation can influence the characteristics of your stimuli. I also hope that you will find comfortable discussing your research requirements with our staff scientist team so that we can guide you through the decision-making process. And in conclusion, I will also share a short document that I've created with guidelines on how to describe and report how you've installed your projection system in research papers. This will help ensure that your setup can be more easily replicated by your colleagues. So instead of writing this in your methods section, during the experiment, we displayed the stimuli with a ProPix projector on a rear projection screen. You'll instead write something like this and understand why it improves methodological replicability. So thank you for watching these videos, and let's start learning about the fascinating world of projection systems. In this section, we will explore the question of what projector technology is needed to create stimuli. We'll begin by examining the stimulus we want to generate and by understanding the hardware requirements. I will explain key concepts such as display resolution, refresh rate, but also projector light engine and imaging technology. First, let's take a closer look at the spatial content of an image. On any computer-driven display, an image is made up of pixels. A pixel is the smallest physical element of an image, and pixels are arranged in a grid. When you program your stimulus, you assign the pixel values on a matrix, and the indexed location will correspond to their spatial location on the physical display. For example, if we wanted to create a display that's defined with this binary data, we would need a physical display capable of displaying a minimum of a 5x5 pixel grid or any multiple thereof. So that binary information could be converted into a physical stimulus. When a display can support more pixels, for example, going from a 5 by 5 to a 25 by 25 grid, we can create increasingly complex images as each of these physical pixels can be addressed individually. So, when we say that a display has a higher resolution than another, we mean that it has a higher number of pixels than the one we were comparing it with. The ProPix projector has a native resolution of 1920 by 1080 square pixels, which, in our example, is more than enough to fully specify the dioptic stimuli. Notice here that our stimuli occupy only a small portion of the display's native resolution. We could even use a resolution as small as 700 by 700 pixels without any problem. Notice how I use the term native resolution to describe the projector's specifications. Native resolution refers to the maximum number of horizontal and vertical physical pixels that your projector can simultaneously present. Native resolution is determined by the specific imaging technology used in a projector. The ProPix projector is equipped with a powerful RGB LED light source comprising 3 independent light-emitting diodes. The wavelengths of these LEDs were carefully chosen to closely match the peak sensitivities of color photoreceptors. During operation, the RGB lights rapidly turn on one after the other, and the combination of the 3 color channels appear as white light. We adjust the LED currents to calibrate the white point of the projector to D65. It's important to note that the light source itself does not create the image. The imaging technology is responsible for converting the pixel information received from the computer into the appropriate spatial layout. The ProPix projector uses a digital micromirror device, a DMD, which is a small chip measuring a few centimeters. That chip is made up of an array of 1920 by 1080 mirrors with 1 micromirror per pixel. These mirrors can be in one of 2 states, on or off. When on, they direct light towards the projection lens, and when they are off, they direct the light towards a light sink. The light sink is an area in the projector that traps the light and minimizes the amount of undesirable light that may escape from the projector lens. For any given image, the micromirrors corresponding to our black pixels will be in their off state most of the time, while our white pixels will be on their on state most of the time. To display intermediate levels of gray, the mirrors must oscillate with particular timings. Our team has developed various sequencers that specify the timing of these oscillations. The mirrors move through microstatic electricity, and this process is extremely fast, with each mirror oscillating about 10,000 times per second. This gives us the flexibility to create very precise sequencers tailored to different research applications. All right, let's get back to our stimulus requirements. We have determined that the ProPix LED DLP projector with a native resolution of 1920 by 1080p is suitable for presenting stimuli with high enough resolution. However, since we wanted to develop a stereo acuity test, we needed to display stimuli with a depth component. So now we need to figure out how we can implement it on a projection system. In the 3D world, when you fixate on an object, you converge your eyes so that its retinal projection falls on the fovea. If you continue fixating on that object, the retinal projection of an object closer to your head will fall some distance away from the fovea. and the relative distance and direction from the fovea will differ between the two eyes. This is called retinal disparity. And retinal disparity is a binocular cue used by the visual system to infer the relative depth of that second target. When doing a projection, it's impossible to physically move the location of the target, so the retinal disparity must be simulated on the screen plane. To simulate a dot appearing in front of a projection screen, you need to ensure that the appropriate retinal projections are maintained. This means that the image that was intended to your left eye should be displayed on this part of the screen, while the target for your right eye should be displayed on that part of the screen. It is crucial that your left eye does not see the image meant for your right eye, and vice versa. To achieve this, we need a mechanism that can implement these requirements. With a Propix projector, the best way to achieve this is to use a DEFQ 3D polarizer or 3D polarizer. It's a piece of extremely rapid electronics that is inserted just in front of a projection lens before the projected light hits the projection screen. The polarizer receives a synchronization signal from the Propix projector that instructs it to switch between two states, a clockwise circular polarization or a counterclockwise circular polarization. The 3D polarizer generates dichoptic stimuli with a method called alternate frame sequencing. The left eye and right eye images are temporarily interleaved such that you regularly switch between a left and a right eye image. The projector beam hits the projection surface, and at that point, the image can be viewed for the first time. However, you can't just project on the regular screen, otherwise the light will be depolarized or lose the induced rotation. It is critical that the screen material selected is passive 3D compatible. Otherwise, the light will be randomly depolarized. But even if you looked at the passive 3D compatible screen without any specialized eyewear, you would not see the depth stimulus. What you would see instead is both information spatially superimposed. So, to ensure that the left and right eye images reach the intended eye, the participant must wear a pair of passive circular polarization filters that selectively only let through either the clockwise or counterclockwise polarized light. So now you know the principle of operation behind a 3D circular polarizer. However, you can't just expect to plug it in and suddenly see the stereo stimulus. You also have to make sure that your stereoscopic stimulus is implemented according to the requirements of the video mode. Before discussing video modes specific to presenting stereoscopic information, let's define video modes more broadly. Generally, video modes are specific combinations of settings used to display images on a computer screen and specify characteristics such as resolution, refresh rate, and bit depth. All visual displays support one or more video modes, and for example, on a Windows operating system, you could access a list of available video modes by right-clicking on the desktop, selecting the display you want to examine, clicking on the advanced display setting, and then enlisting all modes. Well, where do video modes originate? The video protocol used to transmit the video signal from a graphic card to a display sets an upper limit to the rate at which information about the composition of an image can be transmitted during a set period. The Propix projector uses dual link DVI, which means that at its native 1920 by 1080p resolution, it can receive 120 independent images. In other words, every image comprises over 2 million pixels, and each of those can be refreshed 120 times per second. That means that information about the content of 250 million pixels is transferred every second. Moreover, each pixel is described by a 24-bit code, broken down into 3 8-bit triplets used to define the amount of red, green, and blue, which would make up a specific pixel's color. So, to describe the content of a rapidly updating display, one needs to manage a large amount of data per second. If you went back into your operating system and looked at the monitor's available video mode, you would notice two things. First, that the maximum proposed resolution never exceeds the native resolution of the display. But moreover, if you were multiplying the resolution of a specific refresh mode by its refresh rate and bit depth, you would never obtain a larger number than the one that you calculated from the native video mode. What about the standard video modes available for the Propix? You will notice that if you select a smaller image resolution, you can also select a faster refresh rate. Earlier, I mentioned that you can draw your stimulus with a resolution as small as 700 by 700 pixels. Due to this low resolution requirement, you could use any of the low resolution modes for your experiment and increase the refresh rate to update the image content up to 240 times per second. In summary, the video protocol sets an upper limit on the amount of information that can be transmitted over a given period of time, and video modes provide important details about the formatting of the video signal sent to the projector, and it is often possible to trade off certain characteristics of an image for others. Now that we have talked about how video modes are implemented or work in general, let's turn our attention to video modes that are specific to implementing stereoscopic or dioptic information. How does the 3D polarizer know that it should switch between clockwise and counterclockwise polarization? It has to know when the intended image for each eye has arrived, and then switch according to the target left or right image. The 3D polarizer receives the synchronization signal through a direct connection to the back of the Propix projector. The synchronization signal is emitted by the Propix in accordance with the selected advanced video mode. In the simplest implementation, you can set up the Propix in its native video mode and display a new full-resolution image at 120 Hz, so every 8.33 milliseconds. So, we could synchronize the 3D signal such that we alternate between a left and a right eye image every other frame. So effectively, new stereo pairs will be presented sequentially every 16.66 milliseconds or so effectively at 60 Hz. We could also use a lower resolution, as we've mentioned, at 240 Hz, receiving a new pair every 8.33 milliseconds, so effective duration per eye of 4.16 milliseconds, which means that effectively our display would run at 120 Hz. But we have even more advanced video modes, such as our advanced RB3D mode, that enables displaying stimuli at the native resolution of the projector, but at 120 Hz per eye. In this mode, color channels are sacrificed, and the red channel is interpreted as an 8-bit grayscale pattern for one eye, while the blue channel is interpreted as an 8-bit grayscale pattern for the other eye. RB3D mode ensures rapid alternation of the left and right image contents within the span of 8.43 milliseconds, guaranteeing the presentation of stereo pairs and robustness against frame drops. I hope that this gives you some insight onto why it is important to specify the video mode used in a research paper. It's an integral part of the description of the technical characteristics of a projector-based experiment, and when you take it in conjunction with the light source and imaging technology of the projector, it can give your reader the keys to greater understanding, for example, of the exact temporal dynamics of a stimulus. During this section, we learned about a few important concepts that relate to projector technology. We learned about native resolution and refresh rates, about light engines and imaging technology in the form of LED light sources and digital micromirror chips. We learned that some projectors support passive 3D, just like the ProPix, but the specific way the light pattern is structured, with or without the polarizer, is best described by the video mode and not by simply reporting the native resolution and refresh rate. In the first part of this presentation, we identified what projection hardware we need for a specific experiment. At this point, before proceeding to purchase, I recommend that all researchers take some time to carefully document and evaluate the space in which that projector would be installed, basically where they plan to conduct their research. To do so, I want to equip you with essentially a mental checklist that will allow you to actively gather critical information, and that'll be really useful when it comes to time to finalize that installation. As a minimum requirement, you should measure the room's width and depth and mark odd nooks and crannies. You might also want to measure the ceiling height. Then, if the dedicated space has a door, where is it? How wide is it? And in which direction does it open? Are there any windows? This is most common in sound booths, EEG rooms, and non-human primate rooms. Are there any permanent fixtures, like any immovable pieces of furniture or equipment that we might need to work around? So note, measure, and place everything in that floor plan. Then it's really useful to think about just broader considerations and how you work within the room. So instead of just structural concerns, more functional concerns. Think of the normal testing workflow. How do you expect your research assistant to interact with the participant? As you imagine their interactions, do you imagine they'll need to take into consideration additional equipment and not just a projector, another piece of furniture? So keep in mind that the more functionality you want to fit in this space, the fewer layout options you'll have when we tackle the last part of the process, figuring out exactly where all of the projectors and other equipment will be installed. As you imagine the workflow, it's useful to break the interactions in two phases: what happens before the study and during the study. Before the study, consider whether you need to fit in a desk for completing consent forms and questionnaires, or maybe you have another separate space that can be dedicated to this functionality. How does the research assistant start the experiment? Must a stimulus PC also be in the same room? During this study, ask yourself, where is that participant? And what are they doing? Are they sitting, standing, on a moving platform? Does the research assistant stay in the room and need their own desk and chair? And if so, must we also account for a room divider to hide the research assistant from view? If the research assistant can stay outside the room, how are they monitoring the participant? Is there a fixed camera sending them a video feed from a particular viewpoint? Should you make sure that the research assistant can see the participant from a one-way window? If you're able to answer all of these questions related to structural and functional considerations, you will be in a very good position to move on to finalize your installation. However, that's a very simple scenario. There are also some very specialized environments where you might have other additional considerations and other notes to take. If you plan to conduct your testing in a specialized facility, such as an MRI or an MEG room, you will need to start by obtaining a technical floor plan of the room. And that plan will answer most questions regarding the structure of the testing facility. Then, in most specialized facilities, the workflow is somewhat predictable. In MRI, for example, the participant is greeted in a room that's in or adjacent to the control room, right here. Before and during testing, research assistants and technicians will visually monitor participants through the shielded window, right here. Often, there is also a camera installed at the back of the room, in this area. When the participant is ready, they will come in through the side door, lie down on the patient table, and are placed into position inside the MRI scanner. Their head will be at the isocenter, so they're placed in the magnet where the field is strongest and most uniform. And then the participants will be looking straight at the ceiling, but instead of seeing plastic, they will see visual stimulation, but typically through a mirror that's mounted on the head coil that records the bold signal. So now the question is, how do we stimulate the participant using a projector? Well, the MRI environment comes with its own sets of additional considerations and questions. These are, what is the bore length and size? Where is the 10 millitesla or 100 Gauss line? Will you need a mirror to redirect a projection? And is there any space at all within the magnet room itself to install the projector? Now, about deciding on the projection screens, there are two common options. You can install the screen internally, assuming that there's no additional equipment in there that's incompatible with the installation of the projection screen. That typically gets us about 50 to 60 centimeters closer to the head of the participant than if a screen was installed outside of the bore itself. Of course, installing a screen completely outside the bore might be easiest, but that leads to a viewing distance that can be typically a meter and a half away from the participant, depending on scanner design. So there is a trade-off between viewing angle and ease of installation. Scanner models dictate the maximum projection screen width we can use. Let's look at what a screen at the back of the bore or even inside the bore would look like from the viewpoint of the participant. The widest usable part of a screen on a 60 centimeter bore could ever be 60 centimeter wide. But how you use all of that width is up to you. You have the option to choose how you want to project images onto the screen. If you fill the bore, you maximize the field of view. But if you try to project the largest rectangular image possible without any clipping, so within that semicircular space, you will maximize resolution. For example, if you project to fill the bore on a screen, that will result in fewer pixels per degree within the central 20 degrees of the visual field, compared to if you were using the same projector to project a rectangular image. If you aim to measure finer thresholds with the same projector, then maybe you'll decide to opt for a rectangular projection on an internal screen. There are also other special considerations that are very relevant to MRI facilities. In MRI rooms, there is an electronic equipment safety line into which the MRI-compatible version of our ProPix projector should never go. The ProPix should always be installed behind the 100 Gauss or 10 millitesla line, which is specified on the technical floor plan. When the MRI room is sufficiently large and that 100 Gauss line is far enough away from the back walls, the ProPix can be installed directly inside the magnet room, inside the shield pix, as in pictured right here. In many cases, the room is not very deep, and you will not be able to orient the projector directly to the back of the bore. Instead, you will need to use a high-quality mirror of sufficient size to reflect the projection beam from the projector into the projection screen inside the scanner or on external screen. But what do I mean when I say a high-quality mirror? Well, I'm referring to first surface mirrors that are also known as front surface mirrors or optical mirrors. These are mirrors that have a reflective coating applied directly onto the front surface of a glass or another transparent substrate. Unlike standard mirrors, also called second surface mirrors, who have their reflective coating on the back surface, the first surface mirrors reflect light without going through that glass surface substrate and without creating that typical double reflection that a second surface mirror would create. This reflected image that is reflected by a first surface mirror is more accurate and has less distortion than that of a standard mirror. First surface mirrors are commonly used in applications where image quality and precision are important. If you encounter a mirror in a specialized setting, there's a high chance that it could be a first surface mirror. However, you should always verify because it is not guaranteed. If you have a mirror on hand in place and you want to verify whether it's a first surface or a second surface mirror, you can do it yourself with a very simple test. Take a pen or a narrow object and very delicately touch it on one of the peripheral parts of the mirrors. Okay, and you choose a spatial location to avoid damaging first surface mirrors. If you see that the reflection of the pen touches the real pen pretty much directly, then it suggests that the reflective coating has been applied to the front surface of the mirror. However, instead, if you see an empty space between the pen and its reflection, like the left side picture, then that suggests that there's a piece of glass or other protective material that's applied on top of the reflective coating and that you are in presence of a second surface mirror. Why do I say suggest? Well, I say suggest because if your mirror is reflective on both sides, there's actually a really high likelihood that you installed your projector backwards or you tested the wrong side. So make sure that you use that pen test on both reflective sides of your mirror. One of them might just end up being a first surface mirror. So earlier I mentioned that there are some circumstances where it's possible to install a ProPix projector inside the magnet room with a shield pix. However, if the field line, the 100 Gauss field line, is too far away from the scanner, too close to the backlight, it won't be possible to put the projector in the magnet room. You'll have to put it in the equipment room. And how do you get the image inside of it? Well, it's more and more common to see projection waveguides inside MRI rooms. They're also called video waveguides. And they're typically long and wide cylinders that provide an opening through the magnet room shielding. So a little bit like this. It can be hard to visualize in 2D, so let's look at a 3D rendering of that same space. Notice that as we're walking towards the back of the scanner, we see the mirror, then we see the waveguide protruding inside the magnet room, and then we see the back of the projector emerging inside the equipment room, fully outside of the magnet. It's critical to measure the width and diameter of those waveguides and where it's located specifically in the shielded wall. As a rule of thumb, waveguides are designed as this. Their length to diameter ratio is typically around 4:1. So in other words, if the waveguide is about 60 centimeters long, it will need a diameter of about 15 centimeters. That ensures that if the magnetic field was very strong at the level of the shielded wall, that the magnetic field is still constrained within the room and will not damage equipment and devices in the equipment room. Now, when you finalize the projection layout, it's also important to make sure that the waveguide itself is large enough to let the image through unclipped. Finally, I also want to emphasize that we cannot rely on the rule of thumbs to establish a likely location for that 100 Gauss or 10 millitesla line. The reason is simple. Scanners can be quite different from one company to the other, and the rooms within which they are installed are different too. Some scanners, even with the same models, are heavily shielded, and the strength of their magnetic field drops off very rapidly from the isocenter. Some scanners are more lightly shielded, and the magnetic field is still too close or above 100 millitesla, even as it reaches the back wall. In addition, some rooms are very small, leaving very little room to walk around the scanner, and some are much larger, leaving even 3 or 4 meters behind them. So that really underscores the importance of looking specifically at your own specialized testing facility. So, to recap this last section. This time we took an objective look at our testing facilities, and we identified whether there were structural and functional constraints that will guide our choices on where to install our projection systems. We acknowledge that if we work in a specialized environment, we might not have much choice about structural and functional factors, but there might be factors related to the specialized facilities that we need to note. Is there a specific viewing setup, projection clipping and occlusions, whether we need to be mindful of waveguides, and so forth. In the first part of this presentation, we identified what equipment we need to implement our research. Specifically, we figured out the technical specifications of the projection system and established that a ProPix projector operating in RB3D mode with a 3D polarizer accessory would allow us to display our stereo acuity test. Then, in the second part of this presentation, we took a critical look at the physical space where we planned to run our experiments. And it's now time to examine, concretely, how we will finalize the installation of our projector within our testing space. Let's imagine that our experiment will need to be run in a small testing room measuring 2.6 meter wide by 3 meter deep. If we look at the structural concerns, we see that there are no windows, no additional obstacles, and that the door is located in the lower right corner, opening inwards towards the right side wall. The ceiling itself is 2.6 meters tall. Functionally, our participant will be sitting in a simple chair. They will input their responses using a button box, and we won't need the desk that's pictured here. The projector and the PC will be installed directly in the testing room in a corner, as well as will be the testing computer. The research assistant does not stay inside the room during testing. They have an adjacent space where they review the consent form, so we do not have additional details to consider. Basically, this is a small room where only one part is unusable, but it will be relatively straightforward to work with. In this room, from experience, I can tell that there are at least 3 potential layouts that will work. We'll examine them one at a time and do the corresponding calculations. And at the same time, we'll use this as an opportunity to introduce key projection geometry concepts. So our first example, we're going to look at the simplest installation that we can do. It's a rear projection system. On the lateral left edge of the room, we have a maximum of 3 meters to work with. We need to ensure that our participant can come in the room, sit down, and that the projector can be placed with sufficient airflow clearance. With the ProPix projector, you can achieve different image sizes at different projection distances using one of the multiple lenses models that we carry. But how do we find out which of the available lenses, if any, will work for our layout? To start, we need to calculate the lens required throw ratio from 2 other measures, the image width and the throw distance, where the throw distance is the distance between the lens and the projected image. The throw ratio is calculated as throw distance, TD, over image width, IW. What does that represent? You can think of the throw ratio as the distance at which you'll be able to project a 1 meter wide image. So a throw ratio of 2.4 produces a 1 meter wide image at 2.4 meters from the projector, while a throw ratio of 14.83 produces a 1 meter wide image at 14.83 meters from the projector. So, throw ratio is inversely proportional to image size. The larger the throw ratio, the smaller the image will be. From our floor plan, we can roughly measure what the expected throw distance between the lens and the screen will be, and that'll be around 1.22 meters. Ideally, we'll take a little shorter throw distance than that, just to make sure that we have a bit more airflow behind the projector though. But we'll work with 1.22 for now. So now, what is our required screen size? Well, let's return to our original research requirement. If we wanted the central portion of the screen to cover 20 degrees of visual angles, and we wanted our participant to be seated at around 57 centimeters from the screen, it means we'll want the central part of that display to measure about 20 centimeters wide. And since we've already identified that our stimulus is drawn on the central 700 by 700 pixels of a full HD ProPix, we see that this is about 36% of the total display width. Therefore, we'll want to choose a lens that allows us to project a full width image measuring 55 centimeter wide. Next, we calculate the throw ratio as throw distance over image width, where 1.22 meters over 55 centimeters is equal to 0.22. And if you look at the list of available lenses on the ProPix ordering information page, we need to find a lens that supports this value. And we find that one has a focus range, or an official focus range, of 1.22 meters to 9.75, and a throw ratio range of 1.86 to 2.4. So that lens is the fourth one on our list. That means that in theory, this lens fits both our requirements. However, we are planning on projecting at the very short end of the focus range, 1.22 meter, and ideally a little bit closer than that. So before we settle on this choice, we might want to see in practice if that can be obtained. Official lens specifications from lens manufacturers do not always match up with the characteristics of the lenses once they're installed on any projector. In particular, too, the optics of those lenses are sometimes very sophisticated, and there's little interdependencies between throw ratio and focus range that are best looked at in practice. So, for example, if we look at the 1.85 to 2.4 lens mounted on our ProPix with our custom brackets and verified the range of in-focus image size that we can produce at various distance, you can see that in the case of this one, the real image sizes achieved are a few centimeters wider than predicted from the official lens specifications, but we can also easily achieve in-focus images at 1.22 meters and even closer than this if it were required. So that fits perfectly for our setup. Note that the specific pattern does differ from lens to lens. Some cannot achieve all of the theoretical image sizes at the nearest distances. However, we can modify the optics slightly and most often than not bring the focus closer than what's officially printed on lens specifications. So, to summarize, this lens will work perfectly for our setup. After selecting a lens, we now need to select the materials we will use as a projection surface. The characteristics of the material must be compatible with the research requirements as well as how we plan to lay out our equipment. As of May 2024, these are the 4 screen materials that we typically use for our projection screens, and we source them from Stewart Film Screen. 2 of these screen materials, the Film Screen 150 and Silver 5D, are compatible with passive 3D technology and therefore can be used with the 3D polarizers we need to create our stereoscopic stimuli. But what's the difference between a 2D screen and a passive 3D screen? Screens that are intended for regular so-called 2D projections are typically white-colored. The light from the projector's light source is reflected nearly perpendicular to the screen, relatively uniformly around the normal, regardless of the projection's incident angle. This makes these 2D screens particularly well suited for projections onto large screens and result in even luminance across the screen for an observer sitting directly in line with the midpoint of the projection screen. However, these screens are not able to display dioptic stimuli. Rather than maintaining the circular polarization induced by the polarizer, it randomly depolarizes the light once it hit the screen. This results in unacceptable crosstalk for 3D applications. On the other hand, screens intended for 3D projections are typically gray or silver colored. They conserve light polarization. However, they do not efficiently redirect the light towards the observer as much as the 2D screens. The screen will be brighter in the center than in the periphery. In addition, it's also recommended to use longer minimum throw distances than recommended for 2D screens. For example, if you return to the previous charts, you would notice that the film screen 150 is recommended to be used at a throw distance that is at least 1.5 times the width of your planned projected image. Since 1.5 times 55 centimeters is 83, we find that our planned throw distance of 1.22 meters or shorter respects this recommendation. But why are there any minimum recommended throw distances? One consequence of shortening throw distance is that it's likely to amplify any hot spotting which may be present in a projection system. Hot spotting is an uneven distribution of light on the projection screen that resembles a bright hot spot where luminance decreases radially from the center of the hot spots towards the periphery of the screen. Screen materials that recommend longer throw distances are relatively more likely to exaggerate hotspot effects. Our ProPix projector includes an optional automated procedure which allows you to minimize the magnitude of these hotspots. To apply the correction, you'll be asked to identify the center of the perceived hotspot, and you will be prompted to collect luminance samples with colorimeter at various locations on the screen. Then the procedure will apply an inverse function that will reduce the intensity of the hotspot and reduce the range and variance of the luminance along this projection screen surface, making the luminance more uniform across the screen. Now, let's examine a different type of installation. What if we had found out that we had required a longer throw distance than could fit lengthwise in the room? One simple option would be to add a first surface mirror, just as we had discussed in the context of MRI facilities. Can first surface mirrors be used with 3D projection systems, though? The answer is yes, certainly. However, you should be mindful of the number of mirrors in your projection path. Keep in mind that an uneven number of mirrors in the projection path will reverse the orientation of the circularly polarized light compared to a setup that has either no mirrors or an even number of mirrors. In practice, this means that if a researcher designed a stimulus for a projector installation that had no mirrors and shared it with a researcher who uses one mirror, the eye assignment will be flipped. The image that had been originally intended for the left eye in the no mirror installation would be displayed to the right eye in the one mirror installation. However, this is easy to account for or to correct for either by providing an option directly in the stimulus design script or by adjusting the ProPix hardware preferences accordingly. Now, let's say we've decided to use a mirror. Before calculating our required mirror sizes, we need to find two measures. First, estimate the expected distance between the projector and the mirror, and two, confirm which lens we will be using in this setup. In this proposed location, we'll estimate that the mirror will be about 1.38 meters from the projector, and since the total throw distance is going to be about 2.6 meters, our required throw ratio is 4.7. We can use a few different lenses, but let's say we'll take the sixth one on our list, which supports a range of 3.3 to 594. When calculating mirror sizes, it's tempting to simply calculate the image width at the planned mirror distance. However, remember that the mirror would not be perpendicular to the projection beam like a screen would, but rather inclined at 45 degrees on this horizontal plane. To avoid severely underestimating the required mirrored width, you can calculate the required width by measuring the length of a line tilted at 45 degrees intersecting with the projection beam. And image height is then calculated based on the farthest edge of the mirror. And finally, to facilitate mirror installation, we recommend that you increase your planned mirror size by at least 10%. Now, let's look at our third and final installation example. So far, I had only showcased rear projection screens and installations where the projector is located behind the projection screen. However, we find that researchers typically initially request front projection screens. Front projection setups are configurations where the participant and the projector are both on the same side of the projection screens. Researchers often believe that this will allow them to use the space of the room more efficiently and achieve larger image sizes. However, the participant's head is likely to occlude with the projection beam. To avoid cast shadows, the participant typically needs to be sitting farther back from the screen than would be required in a rear projection setup. This increased viewing distance often cancels out any gain in image sizes or floor space that the researcher had hoped to obtain with a front projection setup. This is especially true when the participants wear specialized sensors such as EEG caps, OPM sensors, helmets, or neurophysiology recording rigs. Now, assuming that we want to look at this front projection setup, how can we even align the screen with the participant's line of sight while avoiding so-called keystone effects? First, let's describe keystone effects and why they should be avoided. Well, if you were to simply tilt the projector forward, you would notice that the image would no longer be rectangular, but it would become an isosceles trapezoid. This is what's called the keystone effect, as this shape is reminiscent of an architectural keystone. The goal of a keystone correction is to rectify the image to return it to its original rectangular shape. To do so, you would apply digital image warping to reassign the information from the original pixel locations to their new warped location. However, notice that the keystone effect caused the higher pixel density at the top of the display than at the bottom of the display, and that pixels are no longer square. Reassigning pixel information to the new location cannot occur on a one-to-one remapping and is likely to produce visible aliasing, especially if a stimulus featured high contrast, straight vertical lines. Appearance of aliasing can be minimized by applying anti-aliasing on consumer projectors or on the image pipeline. Anti-aliasing often consists of some level of blur that modifies pixel values, often averaging pixel values in a 2x2 pixel grid at minimum. Keystone correction is a digital solution to correct an optical effect. It will alter the appearance of the final stimuli compared to what you had initially coded, and we find that it's typically inappropriate for vision research. Therefore, we do not include it as a feature on the ProPix projector. Instead, for the ProPix, we offer an optical solution called a lens shift. To change the projected location of the screen, we do not tilt the projector. Instead, we physically change the position of the lens relative to the digital micromirror device and the projection beam. Most of the lenses we carry support a maximum 120% vertical and 30% horizontal lens shift. This means that when the lens is set at origin, the projected image can be moved 60% of its height towards the top of the projection screen, or 60% down towards the bottom of the projection screen, and 15% of its projected width to the left or to the right, without distorting the shape of the projection and the pixel size. Let's look at a concrete example. In this image, we want to achieve a front projection system, but we need to raise the projector above the participant's head, or in other words, lower the screen relative to the projector. Because, as you can see, the participant's head occludes the beam and casts shadow on the projection screen. And here in this case, the head is represented by a green rectangle that stands for a 99th percentile human male skull's height and depth. And while that seems like a conservative measurement, it does not account for hair, specialized sensors, or anything that might take more volume in this space. So how high can we actually raise the projector? Well, in our example, returning to our stereoscopic stimuli, we wanted to project a 16:9 image that would have measured 55 centimeter wide by 31 centimeter tall. 60% corresponds to the ability of raising the propix by about 18 centimeters. But even raising the projector by 18 centimeters doesn't fully solve our problem, because the head still occludes the projection beam. We could have our participants sit below the screen and look up towards the screen, but that wouldn't be very comfortable. What we can do, however, is check whether there are other screen sizes and viewing distance that would cover the same field of view, but allows us to avoid cast shadows. Playing around with the geometry, you can find that the same research requirements can be met in a front projection view, but by using a much larger screen. In addition, the participant would now need to be sitting about twice as far away from the projection screen than the previous layouts. In conclusion, after carefully examining the technical specifications that were required for our stimuli and the physical spaces that we'll be using for experiments, we've identified at least 3 potential installation layouts for our projector within that testing room. The final decision will depend on budget, impact on desired stimulus characteristics, and desire for flexibility. Regarding budget, the first example is a direct projection, and compared to example number 2, requires no mirror accessory. This first example also requires a smaller and less expensive screen than the third example. What about impact on stimulus characteristics? Well, in 3D polarization projection, brighter projections are more desirable, as both the polarizer and the passive filter glasses block out a significant portion of the light that will reach the participant's eye. Given the same projector light source intensity, smaller projected images will be brighter than larger projected images. Therefore, examples 1 or 2 would likely be preferable to example 3. Finally, flexibility and future-proofing can be an important consideration. If we examine the second installation, we see that it meets the current projection needs for a 55 centimeter wide image. However, what if we had a second research stream later on that required much smaller projection with a much higher pixel density? Well, it could be very easy to achieve this goal without any additional accessories. It would be sufficient to shorten the throw distance by removing the projection mirror and reorganizing the equipment, more similar to this first example, in order to achieve a much smaller image. Now that you've learned how the details of projection installation can influence the characteristics of your stimuli, I want to provide some guidelines on how to describe projection installations in research papers. This will help ensure that your colleagues and future readers can more easily replicate your setup. So let's take a moment to review the reference sheet I've prepared for you. The sheet is designed to be taken back to your research laboratory to help you document your projection installation thoroughly. These guidelines encourage you to document 4 aspects. First, the technical specifications, then the installation details, the subject-specific details, as well as the accessories, any additions that may affect the projection and viewing characteristics. This reference sheet also includes a description template suggesting how to formulate this information in a compact way. If we revisit the projection system we discussed during the presentation, the key details would look like this. Regarding the technical specifications, we document the specific projector model, the imaging and light engine technology, and the specific video sequencer used for stereoscopic stimuli. As for the installation details, we document the throw distance, the projected image size, and the screen material. Regarding the subject-specific characteristics, we talk about the viewing distance and the relative position of the participant with the screen. And finally, we discuss the use of a 3D polarizer as a significant accessory in our projection system. This would culminate in a comprehensive yet compact description of your projection installation. So I hope that you find this reference sheet useful for documenting everything about your projection system, as this accurate documentation will improve the reproducibility of your research. And thank you for watching these videos, and please feel free to reach out to our staff scientist team if you have any question or need further assistance with your projection system setup.